Hi, thank you. I'm going to tell you today about a project that we're doing in Australia, basically to track and recover meteorites, to track them using cameras so that we can plot them back in the solar system and work out where they came from. Initially, this isn't new. This isn't a new concept. The idea of fireball networks actually goes back about 60 years. But initially, it was designed simply to recover more meteorites. Back then, we didn't have that many meteorite finds from deserts, so it was really only the falls that people can analyze. So they wanted to get more meteorite finds. Recovering meteorites with orbits, though, gives us a context for interpreting their composition. I started out as a geologist, and it's a basic piece of information that you know where a rock comes from. You can go back to that outcrop and find out things about it. But we don't have that for meteorites. They're a random sample, so it's a way of getting to that information. There's specific science targets that we can get at using systems like this, where the large debris streams exist. And people have also observed and modeled fireballs that may be from cometary streams like the Taurids or the Geminids. So if it was possible to recover one of those, you've basically got a cometary sample, a large cometary sample in your hand. A big deal with doing these kind of networks is to get decent timing on the fireball as it comes in. Initially, we ran a trial program in Australia with kind of giant film cameras, which out in the middle of the desert in Australia, trying to keep something like that running is actually quite difficult, and very expensive. So what we went to is, when we upgraded the system, are liquid crystal shutters just under the lens, which flicker on and off, and usually you can just count those flickers to get a velocity. But if we embed a unique timing signal in that sequence called a De Bruijn sequence, basically you can get, it's like you've embedded absolute timing in a long exposure. So it means that we can get sub-millisecond precision on each segment of our fireball. So we can not only get velocity, but we can get timing in the same image, which makes automating the data reduction a lot easier. So this is what one of our stations looks like. We set them up literally in the middle of nowhere in Australia, well, actually next to a sheep station or a cattle station, which is in the middle of nowhere. And a couple of solar panels, flat pack steel frame that we can set up. We can set them up in about 2 or 3 hours. And they sit there for over 12 months in that kind of environment. They store all the imagery that we get over that period. So the cameras are repeatedly taking 30-second exposures, so about 1,000 images a night. They tell us when they've seen a fireball. We use neural network algorithms to do that. But they store everything. So there's a data set there that I think will be interesting to interrogate for other sciences. This is what one of them looks like. This is our kind of standard desert hardened camera. We've also built a version that's kind of, we've called it a kit system. The initial idea there was that members of the public could basically buy kind of a stripped down thing that they could plug any off-the-shelf DSLR into. And so we got the price of all the other components in there down to about, it's probably about $1,200 US. So it's kind of, you know, amateur observer sort of level. The hard part, in addition to kind of refining all the hardware and getting that desert hardened and checking all of that, good resolution, the timing, the hard part has actually been automating the entire data reduction. That's taken us quite a long time. There's systems that are available to do it for video observations. People have put a lot of effort into that. Not really for still observations. That's a lot more complicated. So we put a lot of effort into that. We're finally there with that, yeah, it took us quite a long time to get it. One of the benefits of doing a project like this versus the other half of what I do, which is meteorite sample analysis, is that Meteorites, you just get a long list of numbers based, trace element compositions or whatever. These we get beautiful pictures as well as really nice data. So, so some of the images are really, really gorgeous. Oh, excuse me. So that's another bright one from a camera in South Australia. In terms of resolution, we can zoom in quite a long way. They're 36 megapixel cameras, so we can track individual fragment trajectories, which is also kind of cute. This is the area that we currently cover in Australia. So Australia is basically the size of the contiguous US. So essentially, if you imagine, swap that for the US. So we cover quite a large area, about a third of Australia. Yeah. Oh, sorry. This is just a snapshot, kind of partway through our data reduction of the trajectories that we've reduced over that kind of southern part of Australia. And this is what all of that reduced data look like. So blue there are fireballs that burned up in the atmosphere. Red are things that all of our data reduction says might be a meteorite on the ground. Basically, by kind of criteria that most people would sign up for, meteorites on the ground. We've not been nearly enough of those places yet, so that's basically our project for the next 6 months. You can see there's kind of a nice. Oh, wait a minute. Is that it? Yeah. Okay. So there's a cluster here. That was the Taurids for last year. Last year was a big year for the Taurids meteor stream. So this is probably a little bit optimistic. I was talking to my colleague Peter Jeniskins about this number, and I think we kind of were a bit optimistic about the brightness that we were seeing. But it's for bright fireballs, it's actually quite difficult to get unbiased data set because data reduction is pretty hard. People have tended to go in using the manual methods, and they've been guided really by high value targets, so things that look odd or where there might be a meteorite attached. So for those fireballs, there's around about maybe something like 800 events in the literature. We're currently up to about 300 with our automated pipeline, so that's going to grow pretty quickly. And because it's an unbiased data set, we can do some interesting things with that. So we have recovered our first meteorite. We did that at the end of last year under kind of interesting conditions on the mud of Lake Eyre. And so this thing came in at the end of November, and we tracked it from a whole bunch of stations. We were able to get a nice trajectory, and we saw that it landed in the middle of Lake Eyre. And Lake Eyre is a huge salt lake in Australia, except when you say salt lake, what you're actually meaning is tiny icing sugar dust on just meters deep of mud. So getting out there to recover that was quite interesting. But that's what the meteorite looked like. It had embedded itself in the mud. We managed to get out there safely and dig it out. So that was a very nice New Year's Eve present. I don't know if I've gone quickly. Okay, good. All right. So where are we? We cover, as I say, we cover about 2.5 million square kilometres of Australia with 50 stations so far. We've got a number of international partners, and we hope that grows in the near future. I think in addition to kind of making the hardware cheap, stable, tough, the data reduction, and we've also got access to a huge supercomputer, data storage, and HPC time. All of those together means that we can actually scale it up pretty easily, which is quite exciting to me. So I think currently we're at 2.5, but we can grow it pretty quickly, which is what the next talk will be about. That data set of fireballs will continue to grow, and hopefully in the near future we'll have gone to many more of those red spots on that plot and found more meteorites. So, thank you.
So right now you run out and recover them yourself.
Yes.
Once you start getting a bunch of these, are you going to have a small army of minions to do this?
Yes, I think that's probably the best way. Yeah.
Okay.
It's and that is actually at the moment that's the least efficient part of the process. So so I think we've got to think of smarter ways of doing that because at the moment, yeah, it's a big field effort.
Yeah, my impression of a lot of your coverage area is it's kind of sparse on roads.
Oh yeah, yes. If anyone's looked at a map of Australia, then you see a whole bunch of things that look like roads in the interior of it, and a whole bunch of names on a map. None of those are roads. They're all dirt tracks. None of the names are associated with towns. They're usually abandoned railway sidings. Yeah, so that's the interior of Australia.
Thank you for your presentation. Two quick questions. One, what are you using for a lens, and what kind of recovery success have you had with tracing down the elements?
No, it's so we in the previous system. So we had this trial with these kind of previous generation of cameras, these film cameras. We had 4 of those, and we ran it for 4 years, and we saw, I think we saw 5 meteorites land, and we recovered 2 of those. This time we've gone on 2 decent trips searching, and we've recovered 1. So I'm going to be, I think I can reasonably say 50% on a given trip. That's. Oh, what sort of lenses? Oh, I'm sorry. So it's a fisheye lens. Yeah, okay.
Hi. So if you know the trajectory of some comet or parent body that might produce meteorites and you can predict these showers, I was just curious if you could use your observations to almost cluster them and basically hypothesize potential parent bodies for certain...
And many people do that, yeah.
Oh, okay.
For comets, absolutely, yes. So many people do that. I think it's one of the things that I'm interested in. There's kind of been a little possibility out there for a long time is can you get asteroidal debris streams? They're predicted not to last very long. A few people who've previously run networks like these have said maybe it's there. If we've got enough data, maybe we can test that. That'd be interesting.
I've got one quick question.
Okay.
What's the time period when you get the information? How quickly can you respond to it?
At the moment, there is a delay in the basically in the reporting from the cameras. So the cameras put their hand up and say, "Okay, we've seen a fireball," but at the moment there's a delay so that we don't get that information immediately. We're fixing that right now. So basically, we'd know, the next morning.
Okay.
That one has landed. Then it's really logistics for getting to that spot. Yeah. For the lake, the logistics were really hard.
Yeah.
For most places, it'd be a lot easier. Yeah.
Great. Thank you, Phil.
Okay.